Hey there, today I'll be doing a walkthrough of question 1 from the 2024 Methods Exam 1. Looking at question 1, this is a pretty stock standard Methods Exam 1 question. We're being asked to find the derivatives of these two functions. The main thing to note here is that this is a Methods Exam 1, so you won't have access to your bound reference. But certain questions will have formulae on the formula sheet that you can use if you get stuck and can't remember the formula that you need. Now we know how to find the derivative of both of these functions, that is e to the x and cos of 3x. And if we can't remember them, then you can see here that they're given to us on the formula sheet. We've got derivative of e to the ax is a times e to the ax, and the derivative of cos of ax is negative a sine of ax. However, in this question, we're not just being asked to find the derivative of these functions individually, we're being asked to find the derivative of the product of these two functions. Now, this should tell us that we need to use product rule. If you remember product rule, then you can go ahead, obviously, and write that down. Otherwise, again, this is also given to us on the formula sheet. So looking at the formula sheet, we've got the product rule here. The derivative of the product of u and v is u times dv dx plus v times du dx. So I'm going to go ahead and write down the product rule for our question, and we can use it to solve it. So we have dy dx is equal to d dx of u times v. For us, we have y equals e to the x times cos of 3x, which is equal to u times v, if u is equal to e to the x, and v is equal to cos of 3x. Now the product rule gives us the derivative of the product is u dv dx plus v du dx. And I'm going to go ahead and compute the derivatives of u and v. So we've got du dx is equal to e to the x, and dv dx is equal to negative 3 sine of 3x. Plugging these into our product rule, we get u e to the x times dv dx, which is negative sine of 3x, plus v, which is cos of 3x times du dx, which is e dx. And we can leave our answer in this form, as this is only a 1-mark question, and we'll attract the 1 mark. Okay, so now moving on to question 1b. In this question, we're also being asked to find the derivative of a function, just like in question 1a. The difference for question 1b being that we're being asked to find the derivative of this function f at a specific point, that is at x equals 3. Just like in question 1a, we know how to find the derivative of a logarithm, a log base e function, and we know how to find the derivative of a cubic function. Moreover, if we've forgotten how to do that, the derivative of these functions is in the formula sheet. So for the logarithm, we've got the derivative of log base e of x is 1 on x. And for the cubic, we don't directly have the derivative of polynomials in the formula sheet, but we have the derivative of x to the n, which is the terms that the cubic is made up of. So we can find the derivative of the cubic by differentiating each of the terms of the cubic separately and then adding up the derivatives. So in that sense, we have the derivative of the cubic in the formula sheet here, the derivative of the power rule. The derivative of x to the n is n times x to the n minus 1. This should tell us that we need to use chain rule. If you remember chain rule, you can go ahead and use that. Otherwise, the chain rule again is here in the formula sheet. We've got dy dx is dy du times du dx. For us, we have f of x is log base e of the cubic, which is log base e of u, if u is equal to x cubed minus 3x plus 2. So going ahead and finding the derivatives that we need, we've got f of x equals log base e of u. This is our y, our function. dy du is equal to 1 on u, because we've got the derivative, y is equal to log base e of u, so the derivative of y with respect to u is 1 on u. And then du dx is 3x squared minus 3 plus 0, or 3x squared minus 3. So plugging those derivatives into our chain rule to find f dash of x, we get dy du is 1 on u, and du dx is So it's that one on u times 3x squared minus 3. Substituting x cubed minus 3x plus 2 back in for u, we get f dash of x is 3x squared minus 3 divided by x cubed minus 3x plus 2. So now we've found the derivative of our function. We want to evaluate it at x equals 3. So we have f dash of 3 equals 3 times 3 squared minus 3 over 3 cubed minus 3 times 3 plus 2, which if you simplify gives you 24 over 20 or 6 over 5. So the derivative of our function f of x at x equals 3, or f dashed of 3, is 6 over 5. Question 2 asks us to consider the following simultaneous linear equations. And it wants us to determine the value of k for which the system of equations has no real solution. So to understand what to do here, it helps to understand what is geometrically going on here. Each of these equations represents a line. So for instance, if I let k equal 2, then I'll substitute k in everywhere you see k in both of these equations, and I'll get two different lines, two specific lines. When k equals 2, these two lines won't be parallel, and so these lines will meet at an individual point, at a specific point, this point of intersection. So this point of intersection, being a point on both of these lines, will satisfy both of these equations, and therefore that'll be the solution to the simultaneous equations when k equals 2. However, if I vary the value of k, then I get two different specific lines. And what this question implies is that there's a specific value of k for which the system of equations has no real solution. What this geometrically corresponds to is when we obtain two lines that don't intersect. Because if the lines did intersect, then that value of xy would satisfy both equations simultaneously at that point, and therefore there would be a solution. So for some value of k, it's the case that these two lines are actually parallel lines. Since they're parallel, they have no point of intersection, and therefore these equations have no real solution. So what we want is two equations representing two lines that are parallel but not the same line, and therefore they won't intersect, and therefore these equations, which represent points on each line, won't have a solution because there'll be no point that is on both lines. So in order to ensure that we have two parallel lines that aren't the same line, it's best to write these equations in gradient intercept form. So that's what we're going to go ahead and do. Writing the first equation in gradient intercept form, I'm just going to label the equations. For equation 1, we get negative 2y equals negative 3kx plus k plus 4, which implies that y is equal to 3 on 2kx plus k plus 4 on negative 2. That's our first line written in gradient intercept form. It has a gradient of 3 on 2k and a y-intercept of k plus 4 on negative 2. So we go ahead and write the second line in gradient intercept form. Ky is equal to negative k minus 4 times x minus k, or plus negative k. And then we can go ahead and divide through by k, and we get y is equal to negative k minus 4 on k x plus negative k on k, which is plus negative 1. So this is y equals negative k minus 4 divided by k times x plus negative 1. So second line has a gradient of negative all of k minus 4 divided by k and a y-intercept of negative 1. So we've now expressed both of these lines in gradient intercept form. For these two lines to be parallel but not be the same line, the gradients have to be equal, but the y-intercepts have to be different. So I'll go ahead and impose those conditions. First condition, so parallel, I'm just going to draw two parallel lines to indicate, this is the parallel condition. So we want 3 on 2k to equal negative k minus 4 over k. And our intercept condition, intercept is that k plus 4 on negative 2 does not equal negative 1. Now I'm going to go ahead and solve for the value of k that makes the gradients equal. So this parallel condition, I need to multiply both sides by k. I get 3 on 2k squared equals negative outside of k minus 4. We can see that this is a quadratic equation, so we're going to want to move all the terms to the left-hand side. So we've got 3 on 2k squared. This is minus k, so here I'm going to have plus k. This is plus 4, so I'm going to have minus 4 equals 0. And then I can go ahead and use the quadratic formula to solve for k. So I have a is equal to 3 on 2, b is equal to 1, and c is equal to negative 4. So the quadratic formula tells me that k is equal to minus b, so that's minus 1 plus minus root b squared. 1 squared minus 4a, which is 3 on 2, times c, which is negative 4. And I divide that through by 2 times a, 2 times 3 on 2. So if we work through the arithmetic here, then we get k is equal to negative 1 plus minus, we've got 4 divided by 2 is 2, so 2 times 3, 6 times 4 is 24, 2 minuses, so we've got plus 24, so this is root 25, and then 2 times 3 on 2 is over 3. So this works out to be minus 1 plus minus 5 over 3, which is equal to negative 6 on 3 is negative 2, or negative 1 plus 5 is 4 on 3. So for these two values of k, we get two specific lines. So two different pairs of lines with gradient either negative 2 each or 4 and 3 each, where these two lines would be parallel. But we also need to make sure that for these values of k, that the two lines aren't the same line, otherwise they'll have an infinite number of solutions instead of no real solution. So for this step, we need to go look at the intercept condition, which is that they don't have the same intercepts. So we need k plus 4 on negative 2 not to equal negative 1. Well, if k plus 4 on 2 doesn't equal negative 1, then k plus 4 doesn't equal 2, which means that k doesn't equal negative 2. So if k did equal negative 2, then they would have the same y-intercept. If k equals negative 2, they would also be parallel, because that was one of the solutions for k for the parallel condition. So when k equals negative 2, they're parallel lines that also have the same y-intercept, so they're actually the same line. And that system would actually just have both equations representing the same line, and therefore there'd be every point on the line is a solution of the equation. So you have an infinite number of solutions. We don't want that. We want no real solutions. So just write this here in green to highlight it. So therefore, no real solutions implies that k is equal to 4/3. So that's the value of k that we need to substitute into the equations. so that the system has no real solutions as required. Hey there, today I'm going to be doing a walkthrough of question 3 from the 2024 Methods Exam 1. So for question 3, this is another quite stock standard Methods Exam 1 question. Question 3a asks us to, this is the graph of a translated truncus, and then in question B we're asked to determine the area under the graph. So obviously that's a calculus question. We're told on the axis below sketch the graph of this truncus. The function is labeled g, labeling all their asymptotes with their equations, so the asymptotes in their equations, and the axis-intercepts with their coordinates. So we take note of the things we have to label on the graph. We then go and calculate the asymptotes and the coordinates, and then after we've done all of that, we can then sketch our graph. Looking at the function g, we can see here that we have a truncus. G of x is 1 over x plus 3 all squared minus 2. The basic equation of a truncus is y equals 1 on x squared. This truncus has been translated 3 to the left and 2 down. If the graph has been translated 3 to the left, we now have a vertical asymptote at x equals -3. So we can go ahead and draw this on the graph. The -2 here translates the graph 2 down, so we now have a horizontal asymptote at y equals -2. And we can go ahead and label that. Okay, now for the axis intercepts, we could start with the x-axis intercepts. We have y is equal to 0, so 0 equals 1 over x plus 3 all squared minus 2. And now we can just invert this equation to solve for x. So this equation implies that 1 over x plus 3 all squared is equal to 2, which means that x plus 3 all squared must equal a half. So x plus 3 equals plus minus square root of a half. So x equals -3 plus minus 1 on the square root of 2. And that's our x-axis intercepts. The square root of 2 is about 1.4, so this is about 1 on 3 on 2. We can go in and label our x-axis intercepts. They'll be about there, -3, plus about 2/3, which is 1 on root 2, and minus 2/3. So now we just need to find our y-axis intercept. We've got a y-axis intercept, obviously when x equals 0. So g of 0 is 1 on 3 squared minus 2, which is 1/9 minus 2. Think of this as -2 plus 1/9, so it's a little bit more positive than -2. Y-axis, so it'll be here. So this is an x value of 0 and a y value of -2 plus 1/9. We can find a common denominator. So this is -18 on 9 plus 1/9, which is equal to -17 on 9. So this is -17 on 9 over here. Now that we've got all our points, we can go ahead and sketch our truncus. Make sure I go through the required points and that I'm going towards the horizontal asymptote but not touching it. I haven't graphed it perfectly. It's a little bit harder in a digital form, but be sure to graph your graphs as accurately as possible on your exam. So now I've sketched this graph. I've made sure it goes through the required points. I've labeled the axis intercepts and the horizontal and vertical asymptotes. Now we can do part B, which part B will be related to part A. So it says determine the area of the region bound by the line x equals -2. So I'm going to go ahead and just draw that on the graph, sketch it. In your exam, you could do this in pencil and then rub it out so that it doesn't appear on the graph because you weren't asked to sketch it, but it just helps you with visualizing the area that you're trying to determine. So here I've got the line x equals -2, I've got the x-axis, I've got the y-axis, and the graph here. So just this section of the graph. And I want the area bounded there, so that's this area here. I want a positive value, but if I calculate the integral, So that'll give me a negative value. So when I take negative of the integral just to get the positive area. Well, the signed area is equal to the integral from -2 to 0 between the line x equals -2 and the line x equals 0, or the y-axis, of g of x dx, but I want the negative of that because I want the actual area. That is negative the integral from -2 to 0 of 1 on x plus 3 squared minus 2 dx. So this is a standard power function integral. We can see that over here in our formula sheet. So in the formula sheet, we've got the integral of ax plus b to the n. In our case, we have a is 1, b is 3, and n is -2, because we've got 1 over x plus 3 all squared. Remembering how negative indices work, and then the formula for the antiderivative is here in the formula sheet. So we can actually just use that to anti-differentiate. So going ahead and evaluating this integral, so we've got negative, and then this is going to become, so using the formula, 1 on a, so 1 on 1, then we've got n plus 1, we've got n is equal to -2, so -2 plus 1 is -1, so this is going to become 1 over -1, and then x plus 3, which is ax plus b, to the n plus 1, which is again -1. So that's our antiderivative, and then we've got a -2 here. The antiderivative of a constant is just that constant times x, so this becomes -2x. And then don't forget the negative at the front, and then we're integrating from -2 to 0. Becomes negative, plug in 0, and we get -1 times 3 to the power of -1 minus 2 times 0, and then minus, and then plug in -2. So we get minus -1, -2 plus 3 is 1. So 1 to the -1 is just going to be 1 minus 2 times -2. There's just a lot of possibility here of screwing up the negative signs. So I'm being very careful about being explicit about what it is I'm plugging in where, and not just trying to do the calculation in one go, and because that's just a recipe for getting the signs wrong. Going up over here, we've got negative the whole thing, so we calculate this. So 3 to the -1 is 1/3, so we've got -1/3 minus 0, and then minus my brackets again. -1 times 1 to the -1 is 1 on 1, which is 1, so this is -1 minus 2 times -2 is +4, and then this becomes negative, so don't forget the negative at the front. -1/3 minus 1 plus 4 is 3, so that -3. You can see inside here, inside the square brackets, I've actually calculated the signed area, and this comes out as negative as it should, so that's a good sign. So we've got -1/3 minus 9/3 is -10/3. So this is minus -10/3, which is 10/3. So then here I'm going to write just in green, so it's clear that area equals 10/3 units squared. Hey there. Today I'm going to do a walkthrough of question 4 from the Methods 2024 Exam 1. So question 4 is from the probability section of the course. More specifically, it's about a binomial random variable. So we're given this binomial random variable x, and it has 4 trials and probability of success 9/10. In part A, we're asked to find the standard deviation of this binomial random variable, and in part B, we're asked to find the probability that x is less than 2. So looking at question A, finding the standard deviation of x, you already may know the formula for this, but if you don't, then if you look at your formula sheet, in the probability section under probability distributions, there's a binomial row, and then there's a column for variance, And it says the variance of a binomial random variable is the number of trials, n, times the probability of success, p, times 1 minus p. And then we should know that the standard deviation is just the square root of the variance. So it's just the square root of np times 1 minus p. So we can write down this, and this is a really simple calculation question. So we have the variance is equal to np times 1 minus p, where n is equal to 4 and p is equal to 9/10. Going ahead and calculating this, we get 4 times 9/10 times 1 minus 9/10 is 1/10, which is equal to 36 over 100, and that's our variance. Therefore, the standard deviation is equal to the square root of that, so the square root of 36 over 100, which is equal to, so standard dev equals this, equals 6 on 10. Moving on to part B, we're asked to find the probability that x is less than 2. So when we want to find the probability of a discrete random variable, the probability that x is less than 2 is the probability that x equals each of the values less than 2 that it can take, because x here can be one of 0, 1, 2, 3, or 4. So if you, for example, a binomial random variable with n equal to 4 and 9/10 probability of success, that could be flipping a very biased coin. So it's 9/10 chance that it lands on head. You flip it 4 times. How many heads do you get? Between 0 and 4. So the probability that x is less than 2 is the probability that x is either 0 or 1. So that's probability x equals 0 plus probability x equals 1. And then the probability that we obtain a certain number of successes is given by the probability mass function for a binomial random variable. And that is, again, there in your formula sheet. So in the formula sheet, under the probability section, we've got the probability distribution for a binomial random variable, and the probability that the random variable x has a certain number of successes, little x, is given by this formula on the right hand side. So we can go ahead and apply this to our question. So I'm just going to write down the formula for the probability that x equals a certain number of successes. It's n choose x, p to the power of x times 1 minus p to the n minus x. Then we can go ahead and use this for x equals 0 and x equals 1. So the probability that x is less than 2 equals the probability that x equals 0 plus the probability that x equals 1. That equals n is 4, so we've got 4 choose 0. Probability of success is 9/10 to the power of the number of successes, which is 0. And then we've got 1 minus p, so 1 minus 9/10 is 1/10. N minus x is 4 minus 0 is 4. So that's the probability that x equals 0. And then we've got to add to that the probability that x equals 1. So that's 4 choose 1. Again, 9/10 chance of success with 1 success. And then 1 minus p is 1/10. The power of n, 4 minus 1 is 3. So evaluating this, 4 choose 0. How many ways are there of choosing 0 things from 4? There's exactly one way of doing that. So that is 1 times 9/10 to the power of 0. Anything to the power of 0 is 1. So times 1/10 to the power of 4. Plus 4 choose 1. How many ways are there of choosing one thing from 4? There's 4 ways. Times 9/10 times 1/10 to have q, 1/10. So, and then we can combine these and get 1 over 10 to the power of 4 plus 4 times 9 is 36 over 10 to the power of 4. This is 37 over 10 to the power of 4. So the probability that x is less than 2 is 37 over 10 to the power 4, or 37 over 10,000. And 37 is a prime number, so we can't simplify this further. And that's our answer to the probability x is less than 2 for 2 marks. Hey there! Today I'll be doing a walkthrough of question 5 from the 2024 Methods Exam 1. So looking at question 5a, at the beginning of question 5 we're introduced to this function h. H of t is 3000 on t plus 1, which models the population of a town after t years. Part A, 5a, is a quite simple question. We're told that we should use the model h of t to predict the population of the town after 4 years. Since h of t models the population of the town after t years, doing this is as simple as letting t equal 4. So the population at 4 years, so pop at 4 years is h of 4, which equals 3000 over 4 plus 1, which is 3000 over 5, which is 600. For question 5b, we're introduced to a new function h1. So we're given at the beginning of question 5, we've been given the function h, which models the population of a town after t years. In part B, we're introduced to a new function h1, which models a different population, where h1 of 0 is h of 0, but h1 decreases at half the rate of h at any point in time. And then we're asked to state a sequence of 2 transformations that maps h to this new model h1. So being asked to find a sequence of 2 transformations that maps one function to another is a standard transformation question. And it's important when you read through the question to work out what the question is asking of you. When you initially read a new function h1 and they tell you this information about it, you don't know why that's important or how you're going to use it. So when I'm reading a question, I try and read through and work out what they want from me. This last sentence indicates that they're looking for a sequence of transformations that maps one function to another. Once I know that, for a transformations question, if I know my transformations theory, I know that I need the formula of the 2 functions to work out how one is mapped to the other. We're given h in the question, but explicitly in the beginning, but the function h1 we're not told about explicitly. So we're given the initial population, we're given h1 of 0, but then we're told h1 decreases at half the rate of h at any point in time. For a transformation question, you're usually given the formulae of both functions explicitly. But now that I know that I need the formula for h1 because I want to find the transformations that map h to h1, now I can go back and reread this information about h1 and understand, I understand that I need it in order to work out what the formula for h1 is. When I read this and it says h1 decreases at half the rate of h, hopefully you register that as being information about the derivative. This is a calculus question, like inside of the transformation question. You're being asked to find the formula for h1 using a point on the function and information about its rate of change. In other words, its derivative. So if we recognize that, then we can see how to find h1. We're told that h1 decreases at half the rate of h, which means that h1 dash of t, the derivative of h1, is half the derivative of h. And now we can work out what h1 is, because h1 of t is equal to the antiderivative of the derivative. And since the derivative of h1 of t is equal to the antiderivative of half of h dash of t, we know our calculus, we know that that's half the antiderivative of h dash of t, but we have h of t, so this is a half 3000 over t plus 1 plus a constant of integration. And so now we've actually found h1 of t up to the constant of integration, and now we can use the point h1 of 0, which is equal to h of 0, which we've been given, in order to find this constant of integration. So the information provided to us about h1 is standard information that would be provided to us in a calculus question, but if we understand that to find a sequence of true transformations from H to H1, we need the formula for H1. We can then go back and look at this information about H1, realizing we want to use it in order to find its formula. And we look at the type of information, and we can see that this is calculus type information about H1. It's information about the derivative of H1. So that's the clue there about what we need to do. So we go ahead now and find the constant of integration. We have H1 of 0 equals a half times 3000 over C plus 0 plus 1 plus C, and H1 of 0 is H of 0, which is 3000 over 0 plus 1. So we've got a half of 3000, which is 1500, plus C is 3000. H1 of 0 is 1500 plus C, which is 3000. This implies that C is 1500. So we've got H1 of T is a half of 3000 over T plus 1 plus 1500. Okay, so now we have the formula for H1, and we can go ahead and determine the sequence of transformations. Looking at H, we have H of T is 3000 over T plus 1. So we've just taken half of that and then added 1500. 1 is dilation by a factor, a half, from, well, it's from the x-axis, the horizontal axis, but we don't have an x-axis in this case because the input variable is t, so it's a dilation by a factor of half from the t-axis. That's what they'll want you to write. They'll want you to use the variables in the question. And then it's a translation, followed by a translation, 1500 units in the positive direction of the h-axis, which is your y-axis in this case. So that's two transformations worth 2 marks. This is worth 2 marks, one for determining h1, and then another mark for writing down the sequence of transformations. So question 5c, the only way that it's really related to question 5a and b is that the question references the same town that we were modeling the population of. So we're told that in this town, 100 people were randomly selected and surveyed, with 60 people indicating that they were unhappy with the roads. In part 1, we're asked to determine an approximate 95% confidence interval for the proportion of people in the town who are unhappy with the roads. So this is a very standard sample proportions question. They've surveyed a certain number of people, 100 people. They were randomly selected, and then they were asked a yes or no question whether they're happy or unhappy with the roads. And now we're being asked to for a 95% confidence interval for the true proportion of people in the whole town, not just those surveyed, who are unhappy with the roads. So for sample proportions, we are given in our formula sheet the formula for an approximate confidence interval. So it's this formula over here in the formula sheet. And we obviously need to use that in our question because we need to provide the confidence interval. So the formula for a confidence interval, I'm just going to write that down at the top, is the proportion of people in our sample, p hat, the sample proportion, minus z, we'll come back to what z is in a second, times the square root of p hat times 1 minus p hat on n, and then the same thing, the upper side of the interval is p hat just plus z instead of minus p hat times 1 minus p hat over n. Okay, so what this says is that if we do a survey like this one, and we survey 100 people, then n will be 100, so 100 people surveyed, and then p hat is the proportion of people in our sample who, in this case, they say they're unhappy with the roads, so obviously the other 40% said they were happy with the roads. So we have p hat is 60 on 100, and then the only other value that we need here for this formula is z. So z is a value that is determined by how much confidence we want. So if you know your confidence intervals, you know that for a 95% confidence interval, z is typically 1.96. But because we want to do calculations by hand, this is a methods exam 1, you don't get a calculator, they say we can use z equals 2 instead of 1.96. Okay, so now that we've got those values, we can evaluate what the confidence interval is. And we'll go ahead and do that, and then I'll talk a bit about what the confidence interval means as well, because this is a oft misunderstood thing in methods. A lot of schools don't spend a lot of time on this section of the course, and I'll take this as an opportunity just to use the question to explain the ideas just a little bit more. Okay, so let's firstly just calculate this confidence interval. So we've got p hat is 60 on 100. We're going to use that for the lower and upper ends of the interval. We've got z equals 2. So what I'm going to go ahead and do is, because we've got this z times this square root thing in both the lower bound and the upper bound for the confidence interval, I'm just going to go ahead and calculate the square root of p hat times 1 minus p hat on n once, and then we can plug it into both sides. So we've got the square root of p hat is 60 on 100. 1 minus p hat is clearly then 40 on 100. And then we've got that divided by n, which is 100. So that gives us, I'm just going to cancel this down. So we've got 6 on 10 and 4 on 10. So that's 24 on 100 on 100, which is 24 on 10,000. So we've got the square root of 24. Just show you that's 10 times 10 is 100. When you then divide that by 100, that's 10 times another 100. So this is square root of 24, which is 4 times 6. So this is 2 root 6 on the square root of 100 times 100, which is clearly 100. So this is root 6 over 50. So this that I've calculated here is the p hat times y minus p hat on n. Okay. And then we're just going to plug all of this, we're going to plug this into our confidence interval formula to calculate the confidence interval. So I'll just write that in green to make it especially clear. So our 95% confidence interval is p hat, which is 60 on 100 or 6 on 10, which simplifies down to 3 on 5. So we've got 3 on 5 minus 2 times root 6 on 50. So the 2 is going to cancel with the 50. So this 2 times root 6 on 50 is 1 times root 6 on 25. So we've got 3 on 5, which is the simplification of 60 on 100, minus root 6 on 25 to 3 on 5 plus root 6 on 25. And this is our 95% confidence interval. Now, if I had to write this in decimals, this would be like 0.6. Root 6 is between root 4 and root 9. So it's between 2 and 3. So 2 on 25 would be about 1 on 25 is 1/25th, that's 0.04, so 4%. So 2 on 25 would be 8%, 3 on 25 would be 12%. So this is maybe about 9%. So we've got 0.60 minus 0.09 roughly to 0.60 plus 0.09. So it's about 0.51 to 0.69. So what is this? This is the approximate 95% confidence interval for the number of people, for the proportion of people in the town who are unhappy with the roads. We're told that a new sample of n people were asked this question, and it resulted in the same sample proportion. So maybe not 100 people were asked this question, randomly selected from the town's population and asked this question about the roads. Maybe a different number of people were asked. And of those n, which is a different number, the same sample proportion, so 60% of those n people, indicated that they were unhappy with the roads as well. And then in 5C part 2, they say find the smallest value of n to achieve a standard deviation of root 250 for the sample proportion. There's kind of a lot to unpack here conceptually. I'm going to spend a little bit of time talking about the concept just before I do the calculation, because this is a part of the course that is often not well explained, and definitely schools often don't spend enough time on it. So looking at our formula sheet, the standard deviation of, so we'll go to the sample proportion section. The standard deviation of the sample proportion is the square root of p times 1 minus p on n. So we have the standard deviation of p hat equals the square root of p times 1 minus p on n. And so we can see here that n, the number of people in the sample, affects the variability of the sample proportion. Now, the other thing that affects the variability of the sample proportion is this p thing. What is this little p? Number proportion of people in the town who are unhappy with the roads. So, for example, if we have 100 people and 60% of people in the town are unhappy with the roads, then the amount of variability that we would have in sample proportions, where the samples have 100 people, would be 0.6, so 60%, times 1 minus p, 0.4, over 100. So we've actually calculated this one before, this square root calculation before, in the confidence interval calculation. And the answer that we get for this is root 6 on 50. So if you repeatedly sample 100 people from the town, and the true proportion of people in the town who are unhappy with the roads is 60%, then the stat calculated before to be approximately 9%. So 9%. So we don't want the standard deviation to be root 6 on 50. We want it to be root 2 on 50. But what are we told in this question? We're told that with the new sample of n people, this results in the same sample proportion. So we still have 0.6 as our sample proportion. Now, for the astute, particularly astute viewers out there, you'll notice that for the confidence interval, when I calculated this square root of p times 1 minus p on n, I didn't actually have p. I didn't have the true number of people in the town, the true proportion of people in the town who are unhappy with the roads. I had the proportion of people in that sample of 100 who are unhappy with the roads, which was p hat. So we can't actually calculate the standard deviation for this, the number of people in this town who are unhappy with the roads, because we don't know what p is. We're going to take this standard deviation of p hat, which equals the square root of p times 1 minus p on n. This is the exact standard deviation for a true proportion of people in the town of p at a sample size of n. And we're going to approximate that with the square root of p hat times 1 minus p hat on n. And that's going to be the standard deviation that we're going to work with. So this question that asks us to determine the smallest value of n to achieve a standard deviation of root 2 on 50 is conceptually a little bit wrong, because saying that the sample that you obtain has a sample proportion that is 0.6 doesn't actually allow you to calculate the standard deviation, because you don't need the sample proportion to calculate the standard deviation. You need the true proportion, the actual proportion of people in the town. But because the sample proportion, assuming there isn't too much variability in your samples, is likely to be close to the true proportion, and so p hat is approximately p. Okay, so that being said, the approximate standard deviation that we want to be root 250 is the square root of p hat times y minus p hat on n, but we're told in this question that this value for p hat is the same as in the previous question. So we should be using p hat equals 0.6. Now, that means that our standard deviation is equal to the square root of 0.6 times 0.6 times 1 minus 0.6 over n. And then we can, with square roots, we can take the square root of the top and the square root of the bottom separately. So we get the square root of 0.6 times 0.4 divided by the square root of n. Now, this calculation looks very familiar because it's exactly what we did in 5C part 1. In 5C part 1, we got an answer of root 6 on 50. But we want root 2 on 50, which is equal to 1 on root 3 times 1 on root 3 times root 6 on 50. Since the numerators in both of these standard deviation calculations are the same, this factor of 1 on root 3 must come from the denominator. That would work if n is 3 times the size, so that we get, if we see this, we get 0.6 times 0.4 divided by 3 times 100. We can then split this into root 3 times root 100. And then in the numerator we have 0.6 times 0.4. But we know that this bit is root 6 on 50. So then we get 1 on root 3 times root 6 on 50, which is root 2 on 50. How did we do that? We made this denominator, square root, 3 times 100. So we need n to be 300. We need to be 3 times as large. Hey there. Today I'm going to be doing a walkthrough of question 6 from the 2024 Methods Exam 1. So for question 6, we're given this logarithm equation. The thing that we want to do is try and combine the logarithm terms using logarithm laws. You know, we're solving an equation here, we probably want to convert it into exponential form. So just going ahead and manipulating the logarithm expression on the left-hand side, I've got 2 times log base 3 of x minus 4. When I've got a factor at the front like 2, I want to use the power law of logarithms to produce, that becomes log base 3 of x minus 4 all squared. So the power of 2 has come down at the front in the original expression. And then it's that plus log base 3 of x, and this is equal to 2. Now I've got the sum of 2 logarithms with the same base, so I can combine those to obtain logarithm base 3 of x minus 4 squared times x. So the 2 results get combined into a product, and that's equal to 2. At this point, you want to turn this into exponential form. So this says this is the base 3, this is the power 2, this is the result x minus 4 squared times x. So this logarithm equation is equivalent to 3 to the power of 2 is x minus 4 all squared times x. So you can see that this is actually a cubic equation in disguise. So we've got this is 9. So we've got 9 is equal to x minus 4 all squared times x. It's great that the cubic is factorized. Unfortunately, the number on the other side is not 0. So in order to solve this cubic equation, we now need to expand the cubic and shift the 9 to the other side. So I'll expand the cubic. I get x times x squared minus 8x plus 16 is equal to 9, and this becomes x cubed minus 8x squared plus 16x minus 9 is equal to 0. So now to solve this cubic equation, we know that we need to find a factor, and we can find that factor using factor theorem by finding a value of x that makes this cubic equal to 0. So trying out different factors of 9, the last term, we start with x equals 1, and I get 1 cubed minus 8 times 1 squared plus 16 times 1 minus 9. So that's 1 minus 8, which is negative 7, minus 9 is negative 16, plus 16 is 0. So that's good. So factor theorem implies that, therefore, x minus 1 is a factor. Now that we know that x minus 1 is a factor, we need to divide the cubic by this linear factor x minus 1 to find the quadratic factor. So to further factorize the cubic. So we've got x minus 1 into x cubed minus 8x squared plus 16x minus 9. X goes into x cubed x squared times. So that becomes x squared multiplying back, x cubed minus x squared. So we've got minus 8x squared minus x squared, which is plus x squared, becomes negative 7x squared. So x goes into negative 7x squared minus 7x times. So we want to now multiply back negative 7x, we get negative 7x squared. Negative 7x times minus 1 is plus 7x. And we subtract the two lines and we get 0, and then 16x minus 7x is 9x. So that comes out to, we need to multiply x into 9x. That goes 9 times, and then we get 9 times x. Here we've got a minus 9. 9 times minus 1 is minus 9, and then it goes to 0. So this is good because we found that there's a 0 remainder, which there should be because x minus 1 is a factor, and then the quadratic factor is the thing up the top here. So we can rewrite this equation over here, this cubic equation. We can write the cubic in factorized form. So this implies that x minus 1 times x squared minus 7x plus 9 is equal to 0. So using null factor theorem, this product is equal to 0 if either x minus 1 equals 0. So this implies that x minus 1 is 0, or x squared minus 7x, that's supposed to be plus 9, is 0. So, or that's 0. So x minus 1 is 0 if x equals 1. That's the root we already found. And then we need to work with x squared minus 7x plus 9. We could try and factorize this directly, but it doesn't look like, so 1 and 9 and 3 and 3 are the factors of 9. None of those give us 7 as a middle term when you add them. So it doesn't look like this can be factorized over whole numbers. So instead we can use quadratic formula. But the other thing that we're interested in here not only is what are the solutions to x squared minus 7x plus 9 equals 0, but are there any? So we can use the discriminant in order to check whether or not this quadratic has x-intercepts, so whether this equation has solution. So we've got a is equal to 1, b is equal to negative 7, and c is equal to positive 9. So the discriminant is b squared, negative 7 squared, minus 4 times a, which is 1, times c, which is 9. So this is 49 minus 36, which is positive, and it's equal to 13. So the discriminant is positive, meaning that there are two x-intercepts. They're just not whole numbers. Okay, so let's go ahead and work out what those x values are. So we've got x is equal to minus b, which is 7, plus minus root the discriminant. So it's b squared minus 4ac, but we've already determined what that is. So that's 13 over 2a, which is 2. So there's nothing we can do here to further simplify this. So those are the two solutions to the quadratic, and then we've got x equals 1. So seemingly these are our solutions to the original equation. The one thing that we need to be careful about is with logarithms. So this x can't be less than or equal to 0. So that's bad. So here x has to be at least 0. And here x, because we've subtracted off 4, x has to be at least 4. Otherwise, the logarithm isn't defined, because there's no power which takes a base 3 to a negative number. Hey there! Today I'm going to be doing a walkthrough of question 7 from the 2024 Methods Exam 1. So question 7, at the beginning of question 7, we're introduced to this function, f of x equals x times sine of x. And the function's domain is negative pi to pi, but we've got a graph here just of the function f of x on the interval 0 to pi. So we don't have negative x values here. In part A, we're asked to use the trapezium rule to determine an approximation of the total area between this graph f and the x-axis. So this is a very standard, essentially integration question, and the formula this is calculus, obviously, and then in the formula sheet under the calculus section we have the trapezium rule approximation, which gives us how to calculate the approximate area using trapeziums. So the formula is over here. So let's just go ahead and sketch on the graph the trapeziums that we're going to use to approximate the area underneath the graph. So just to be clear, the area that we want is the area, total area between the graph and the x-axis over the interval 0 to pi. So we have the interval 0 to pi here, and this area is the bit that I'm shading in red. So that's the area that we would want to calculate. The exact area would be given by the integral of f over 0 to pi, but we're going to use an approximation involving trapeziums. So we're going to take, we use step sizes of pi on 3. So we're going to have one trapezium that goes from 0 to pi on 3. This trapezium is actually a triangle. For the second trapezium, step size of pi on 3, so from pi on 3 to 2 pi on 3, we've got a trapezium here. And then for the third trapezium, it's actually also a triangle. It's a triangle because the value of the endpoint at the other side is 0. Likewise for the first trapezium. So this green shaded area, which is the total area of these 3 trapeziums, or one trapezium and 2 triangles, that is an approximation of the red shaded area, which is the actual total area between the graph and the x-axis. So I'm just going to go ahead and write down the trapezium rule. So the approximate area is equal to, the formula is xn minus x naught over 2n. So what is n here? N here is the number of trapeziums. So we have n is equal to 3. And then x naught is this left-hand endpoint, and x3 is this right-hand endpoint. And then we have x1 and x2 are pi on 3 and 2 pi on 3 respectively. So going ahead and finishing off the formula, we've got xn minus x naught on 2n, and that's times by the value of the function at x naught plus 2 times x1 plus 2 times the function at x2 plus the value of the function at x3. So I can replace this here. This n is actually 3. So this is 3, and this is 3 here. So this is the trapezium rule approximation when we're using 3 trapeziums. So we have n is 3. Just to note the form of the rule, we've got the right endpoint, so most positive value minus the left endpoint x0 divided by 2 times the number of trapeziums. And then we've got that times the function at each function value at each of these points, where we've got the function left endpoint, the function right endpoint. Those are just themselves. And then the internal points So x1 and x2 and any other internal points, if you've got more trapeziums, those are 2 times the function values at those points. So our function values that we have here, we've got f of x naught. We can see the function is 0. Then f of x1 looks like it might be about 1. F of x2, which is f of 2 pi and 3, maybe about 1.8. And then at f of x3 is 0 again. So plugging these values into our formula, we get x3, which is pi, minus x0, which is 0, divided by 2 times 3. And then f of x0 is 0, plus 2 times the function at x1. x1 is pi on 3. So we've got 2 times the function is x times sine of x. This is f of x. So this is equal to 2 times x, which is pi on 3, times sine of pi on 3, plus 2 times the function at x2, which is 2 pi on 3. So we've got 2 pi on 3 for x, times sine of 2 pi on 3, plus the function at pi, which is clearly 0. So plus 0. So we get pi on 6 outside of 2 pi on 3. Sine of pi on 3, you need to know your exact values, is root 3 on 2. Plus 2 times 2 pi on 3 is 4 pi on 3. Sine of 2 pi on 3 is also root 3 on 2. So there we go. That's the approximate area, and then we just go ahead and simplify this. So we've got 2 pi root 3 on 6 plus 4 pi root 3 on 6 is 6 pi root 3 on 6. So this is pi on 6 times 6 pi root 3 over 6. We can cancel the 6's, and we get pi squared root 3 on 6. So this is our answer for the approximate area under the graph of f of x equals x sine x, but between 0 and pi. That's the answer to 7a. In 7p, part 1, we're asked to find f dash of x. So we have f of x is x sine x. We know how to find the derivative of x and sine x separately. If you need, the formula for calculating the derivative of x is in the formula sheet, as is sine of x. We've got a product of those two functions, so we want to use product rule, which again is also in the formula sheet. So going ahead and calculating that, we've got f of x equals x times the derivative of sine x plus the derivative of x times sine of x. So this is x times cos x. Derivative of x is 1. So that plus 1 times sine x is sine x. So f dashed of x, sorry, I meant f dashed of x. F dashed of x, the derivative is x cos x plus sine x. In B part 2, we're asked to determine the range of f dashed of x, the range of the derivative, over the interval pi on 2 to 2 pi on 3. So we've just gone ahead in part B, part 1, and calculated the derivative of x sine x. It's x cos x plus sine x. Now, the thing about calculating the range of a function is if, for example, I give you a line over some interval that has a positive gradient, then you know that the lowest value of the function occurs at the left endpoint, and the highest value of the function occurs at the right endpoint. But if, for example, I give you a parabola on an interval, so I only give you part of the parabola, you have a left endpoint and a right endpoint. If you just calculated the value at the left endpoint and the right endpoint, and you thought that the range of the function was between those two values, you'd miss out this upper section out here, because the function doesn't just increase or decrease. It increases and then decreases. So in order to ensure that you have the full range of a function over an interval, you need to know what kind of behavior it has. So we haven't actually graphed x cos x plus sine x. But what we do have is we have a graph of the function of f. So the interval that we're considering is from pi on 2 to 2 pi on 3. So if we look at the graph of f, then we should work out where pi on 2 is. Pi on 2 is obviously not the same denominator as pi on 3 or 2 pi on 3. So we'll convert all of these in the same denominator so we can work out where they are relative to each other. So 2 and 3 has, we can write a common denominator of 6. So pi on 3 is going to be 2 pi on 6. Pi on 2 is going to be 3 pi on 6. 2 pi on 3 is going to be 4 pi on 6. So pi on 2 is halfway in between pi on 3 and 2 pi on 3. And so that means we're here. This is pi on 2. This is where x is equal to pi on 2. And we can see there that the gradient is positive. And then as we move to the right towards 2 pi on 3, we can see that the gradient is becoming less and less positive. And then somewhere around the top here, around 2 pi on 3, the gradient becomes 0. And then it becomes negative as you keep moving to the right, as x keeps becoming more and more positive. So it must be that we start at pi on 2 and we move to the right. The gradient is its maximum value. The derivative f dash of x is its maximum value at pi on 2. And then it becomes more and more negative the further to the right we move. So because we know that the gradient is strictly decreasing on the interval, we can just calculate the derivative at pi on 2 and 2 pi on 3. The minimum derivative over that interval will occur at 2 pi on 3, and the maximum derivative will occur at pi on 2. So it's much like this line case, where I'm saying that the function, in this case the function is our derivative, is only, in the line case I showed it as increasing, but in our case it's just decreasing over the interval of interest, which is pi on 2 to 2 pi on 3. So going ahead and calculating those endpoints, I'll just do 2 pi on 3 first, because that's the lower bound of our range. So we've got f dash of x, and that's equal to x cos of x plus sine of x, and then f dash of 2 pi on 3 is equal to 2 pi on 3 cos of 2 pi on 3 plus sine of 2 pi on 3. So cos of 2 pi on 3, cos is negative in the second quadrant, and cos of pi on 3 is a half, so this is negative a half. So we get 2 pi on 3 times negative a half, and then sine of 2 pi on 3 is root 3 on 2. So I know that sine of pi on 3 is root 3 on 2, and sine is positive in the first and second quadrant. So this gives me root 3 on 2 minus pi on 3. So that's the lower end of our range. And then we just need to calculate, so I'll just do it up here. We need to calculate the derivative at pi on 2, which is the maximum value. So f dash of pi on 2 is pi on 2 times cos of pi on 2 plus sine of pi on 2. This one's easy. Cos of pi on 2 is 0, so pi on 2 times 0 is 0 plus sine of pi on 2 is 1. So the answer is 1. So the range, I'll just do this in green to indicate that's the answer. The range of f dash of x is equal to, and note that pi on 2 and 2 pi on 3 are included in the domain. So we've got inclusive of those values. So we've got root 3 on 2 minus pi on 3 to 1. And that's the range for 1 mark. Okay, so now moving on to 7b part 3. In 7b part 3, it says hence, so that means that we're going to use our previous answer. Verify that f of x has a stationary point for x as an element of pi on 2 to 2 pi on 3. So obviously, we're supposed to use b part 2, because we're verifying a stationary point in the same interval that we've just calculated the derivative for. What does a stationary point mean? A stationary point means f dash of x is equal to 0. So if we look at the range that we had for pi and 2 to 2 pi and 3, we start off with positive 1, we decrease towards root 3 on 2 minus pi on 3. If there's a stationary point, just looking at the graph, right, at the graph of f, so the function itself, x times sine of x, at pi on 2, it has a derivative of 1, which then decreases continuously. So if it's decreasing continuously, then between pi and 2 and 2 pi and 3, it'll hit 0 if that range contains 0, because it'll start at 1, it'll decrease through every value between 1 and the lower, the most negative value of the derivative on that interval, which occurs at 2 pi and 3. So the thing that we're actually interested in now is, can we reason about what this root 3 on 2 minus pi on 3 is? If it's less than 0, then that means that at pi on 2, the derivative is 1, and then it must decrease through 0, because the derivative is continuous, f dash of x is continuous, on its way to root 3 on 2 minus pi on 3. So pi is 3.14. So pi on 3 must be greater than 1, because a third of 3.14 is greater than 1. But the square root of 3 is less than the square root of 4. The square root of 4 would be 2, so 2 on 2 would be 1. But the square root of 3 being less than the square root of 4 is less than 2, so this is less than 1. So root 3 on 2 is less than 1. So a number less than 1 minus number greater than 1 is less than 0. Therefore, f dash of x equals 0 for some x is an element of pi on 2 to 2 pi on 3. So the key thing here is that f dash of x is continuous on the interval, and that the range of f dash of x, the values that the derivative takes on that interval, is an interval that contains 0. So for question 7c, it says on the set of axes below, sketch the graph of y equals f dash of x on the domain negative pi to pi, labeling the endpoints with their coordinates. So we're being asked to sketch the graph of the derivative. One thing that you could try to do is work out like all of the features of the derivative from the rule. The derivative is x cos of x plus sine of x. But actually, they've put on the graph of the function. So this question is, we're supposed to use f of x, the function which is displayed to us here, in order to determine what f dash of x is. And then the only other thing that we have to do is we have to label the endpoints. Okay, so the endpoints we obviously can't get from the graph of the function, but we do have the rule for the derivative, so we can evaluate the endpoints. And then our derivative has turning points, which we wouldn't be able to determine where they are or what values they have, except these are given to us as approximately negative 1.1, negative 1.4, and 1.1, 1.4, so we can use those in order to sketch our graph. So going ahead, and the first thing I would do here is actually not just go ahead and sketch it, but actually work out what certain points on the derivative will be. So we can see here that it looks like at 0, there's a turning point, so we have a derivative of 0 there, and then again at like approximately negative 2 and 2, we have turning points as well. So expect our derivative to be, I'm just going to do this in green to make it easy to see. So we can see we can see the derivative is 0 at these 3 points because there are turning points in the graph of f there. And then we can see on the positive side, as x increases away from 0, that the derivative becomes positive. And then it becomes more and more positive until some point that it flattens out. So it becomes a maximum derivative at some point around 1. and then it decreases and goes towards 0 at about 2, and then it becomes negative. So we wouldn't know where to put this local maximum turning point here, except we're told we have a local maximum of approximately 1.1, 1.4. So going ahead here, this looks like at about 1.1, and 1.4 is about halfway in between 1 and 2. So that must be our local maximum. And then similarly, we have a local minimum for the on the other side at negative 1.1, negative 1.4. So around here. So that's we're getting a sense of the shape, and now we just need to go ahead and calculate our endpoints. We get f dashed of pi is, so we've got the derivative is x cos x plus sine of x, so f dashed of pi is pi times cos of pi plus sine of pi. Sine of pi is 0, cos of pi is negative 1, so this is negative pi. Cos of pi is negative 1, so this is negative pi. Yes, so we're working at x equals pi, the value of the derivative is negative pi, so pi is about 3.14 down here, so in line with this, and then we need to go a bit under negative 3 because we need negative pi, which is negative 3.14. So we've got our endpoint of our derivative at pi, negative pi, and then go ahead and calculate the other endpoint. We've got f dashed of negative pi, which is negative pi, so x times cos of x, negative pi times cos of negative pi, plus sine of negative pi. So that's actually the same point on the unit circle, negative pi. So cos of negative pi is negative 1 times negative pi is pi, sine of negative pi again is 0. So we've got negative pi, so that means up here, this is negative pi is our other endpoint. So we've labeled our endpoints, and then we can go ahead and sketch this graph of the derivative. So we've got the local turning points, we've got the x-intercepts, we've got approximately, there's nothing, we can't calculate those exactly, and then we've calculated the exact endpoints as labeled them as required for 3 marks. Hey there, today I'll be doing a walkthrough of question 8, the final question in the 2024 Methods Exam 1 paper. Question 8 centers around this function g. It's a cubed root function, so we've got the cubed root of x minus k plus m. And here, k can be any non-zero real number, and m can be any real number. So the thing about this question is that we're essentially being introduced to a family of functions. So the values of k and m, these parameters, will determine which cubed root function we get. And the best way of finding it easy to answer the subparts of this question is to understand what these cubed root functions look like and how the parameters k and m affect which specific function you get. So what I do when I'm working through a question like this is I try and start with the most basic example, like the most basic function of that kind, and then I try and understand how, for example, like in this question, how the parameters k and m affect the actual specific function g that I might be looking at. So they've told us that k is any non-zero real number and m can be any real number. I'm just gonna, for the purposes of understanding what g might look like, I'm gonna let k equal 0 as well, even though, k can't be 0 if it's one of these g functions. And then I'll let m equal 0. And then I get a function, I'm going to call it f of x instead of g, because it's not one of these, but very closely related. And that'll just be the cube root of x, because both k and m are 0. So now, if we've got that specific function f, we can think about what f looks like. So the cube root of 0 is 0, so it'll go through the origin. Then the cube root of 1 is 1. The cube root of negative 1 is negative 1. So we have these 3 points. And then we can either reason about what it looks like, or we can remember this family of functions, the cube roots, and we'll realize that it looks, much like a square root function, except on the negative side, negative x, we also get the negative y. It's an odd function, and so it's going to look like this on the other side. So that's our function f of x, which is the cube root of x. Now that we know that, we can think about what effect the k and m have. So this brings us to our transformation theory. If we have x minus k here, so for example, if we were to introduce a new function f1 of x, which is equal to the cubed root of x minus k, then if k was 2, for instance, the cube root of x minus 2, this would be our cube root function moved 2 to the right. Conversely, if we had, or really similarly, if we had k is equal to negative 2, so we have x minus minus 2 or x plus 2 under the cube root sign, then that would move the function 2 to the left. So what this k parameter does in our g function is it moves the function right and left. And then, pretty easy to understand, the m moves the function up and down. So the cubed root of x minus k plus m is just the cube root of x moved to the right and left and up and down. It's a translated version of just the cube root of x. So this entire question is about functions g that are translations of the cube root of x. Once we have that in mind, the rest of the question is actually quite easy to understand. So now let's look at part A. We're introduced to the function g at the beginning of the question. They say let the point P be the y-intercept of the graph y equals g of x. So what's a y-intercept? A y-intercept is the value of the function when x equals 0. So we want 0 g of 0. That's our point P. Now we have to find this in terms of k of m. So we have to evaluate g of 0. So we get g of 0 is the cubed root of 0 minus k plus m, which is just the cubed root of negative k plus m. So our point P is 0 cubed root of negative k plus m, and that is the answer to this question. That is the point P, the y-intercept, in terms of k and m. If we think about what this means, obviously k and m affect right and left translation and up and down translation respectively. So for different values of k and m, if you move the graph to the right and left or up and down, then that affects where the graph goes through the y-axis. So it makes sense that the y-intercept would be affected by both the values of k and m, which it is. And this is the actual value of that y-intercept in terms of k and m. Great. So moving on to part B, they say find the gradient of g at p in terms of k. Well, the gradient is just the derivative, so we want g dashed of x, and we want it at p, but we find the gradient in terms of the x-coordinate of a point. Since p is a y-intercept, its x-coordinate is 0, so really we're just being asked for g dashed of 0 in terms of k. So to find this, we first have to find the derivative of g dashed of x, and then plug in x equals 0. So going ahead and doing that, we've got g of x, just going to write down g of x so we have it there. It's the cube root of x minus k plus m. We want to differentiate this, so I'm just going to actually express this in standard index notation, because that's how we differentiate powers. And I recognize that the cubed root is just to the power of 1/3. So we've got x minus k to the power of 1/3 plus m. So now to take the derivative of this, m is just a number, so its derivative is going to be 0. So we just focus on the first term. And here we just have a linear function, x minus k, to the power of 1/3. So differentiating this, if you want to, you can use chain rule. So you can write g of x is equal to u to the power of 1/3, where u is equal to x minus k. And then you can just call this y, the function output, And then chain rule tells us that g dash of x is dy dx, which is dy du times du dx times du dx. The derivative of u to the power of 1/3 with respect to u is 1/3 u to the negative 2/3. And then the derivative of u with respect to x is just 1. Again, k is just a constant, so we just differentiate the x. So this is 1/3 u is x minus k to the power of negative 2/3. And that is the derivative of g of x. Now we want this at p. As we said before, p has x coordinate of 0, so we want g dashed of 0. So this becomes, I'm just going to write this below. We've got g dashed of 0. We plug that into our derivative, and we get 1/3 to the negative k. Sorry, 1/3 times negative k to the negative 2/3. So that is the gradient. This is the gradient at p. I'm just going to circle that in green to make clear that this is our answer to part B. So for part C, it says, given that the graph y equals g of x passes through the origin, express k in terms of m. So if the graph g, so it's our translated cubed root function, passes through the origin, then that means that when x equals 0, which is the y-axis intercept, y is also equal to 0. But we already know that the point P is, which is our y-axis intercept, has in terms of k and m, the y value is the cubed root of negative k plus m. But now we're saying that we want this to be 0. So if g of 0 equals 0, that implies that the cubed root of negative k plus m is equal to 0. But then we want to express k in terms of m. So in order to do that, we just need to solve here for k. So we have the cubed root of negative k is equal to negative m. Subtract m from both sides. Now, the cubed root of negative k is negative m, which means that negative k is equal to negative m cubed, which is actually also equal to negative m cubed. So here I'm saying it's negative m cubed. Therefore, k is equal to m cubed. So what this says is that if our graph g of x has a y-axis intercept, which is also the x-axis intercept, passes through the origin, then there are lots of cube root functions that have this property, but that only happens when the horizontal and the vertical translations are coordinated so that k, whatever the horizontal translation is the cubed of the vertical translation, m. So this is the answer, just circled in green, for part C. So that brings us to question 8D, the final part of question 8, and the final part of the final question on the 2024 Methods Exam 1 paper. Okay, so in question 8D, we're told that the point Q be a different point from the point P, such that the gradient of G at points P and Q are equal. Given that the graph y equals g of x passes through the origin, find the coordinates of Q in terms of m. So this is a kind of, not an easy question to necessarily understand what's going on. So the best thing we could do here is try and graph what this graph G might look like. So we've got xy axis, and then we've got this, a cubed root function that passes through the origin. We know that we can't have k is equal to 0, so it's not just the cubed root of x. It's being translated horizontally. And we know that it passes through the origin, so we know that k equals m cubed. So we might have our function look like this. So for example, if k is equal to m cubed, m might be 2. So it's translated 2 up, and then k is equal to 2 cubed, which is 8. So it's being translated 2 up and 8 to the right. So here we might have 2, and here we might have 8, and that's where it's been translated to. And this graph goes through the origin, and then goes across like this. So point P is the y-axis intercept, where it goes through the origin, and we can see that we've got a certain gradient there. And then if we go further to the right, there's another point where the gradient might be the same as at the origin. And this would be our point Q, because it's the point other than point P on the graph that has the same gradient. And this graph goes through the origin. So we want the coordinates of this point in terms of M. We could do it in terms of either M or K because they're related. So going ahead and actually finding it using the information provided to us in the question, we're told that the gradient at Q is the same as the gradient at P. We have the gradient of this function g from part B. We calculated g dash of x. If we name this point Q, so we say its x coordinate is xq and its y coordinate is yq, then we have the derivative at the point Q, which is d dash of xq. That's equal to 1/3 xq minus k to the power of negative 2/3. And then that's equal to the derivative at P, but P is the y-axis intercept, so it has an x coordinate of 0, so that's equal to d dash of 0. And this is equal to, from part B again, 1/3 negative k to the power of negative 2/3. Now, if I take this 1/3 x cubed minus k to the power of negative 2/3, and I let that equal 1/3 negative k to the power of negative 2/3, so the gradient at Q is equal to the gradient at P, I can solve that as an equation for the x coordinate of Q. However, that would give me the x coordinate in terms of k. So to find the x coordinate in terms of m, which is what has been requested of us, we can substitute k in terms of m because our graph passes through the origin, and when the graph passes through the origin, we have k in terms of m. K is equal to m cubed. So we can write down the equation: 1/3 xq minus m cubed to the power of negative 2/3 is equal to 1/3 negative k to the power of negative 2/3. Sorry, we can write that down, but we can also write down 1/3 x cubed minus m cubed to the power of negative 2/3 is equal to 1/3 negative m cubed to the power of negative 2/3. Okay, now I want to solve this equation for x. I don't really like the negative indices. It makes it kind of hard to think about what I'm doing. So I can re-express this in terms of roots. Just before I do that, I notice that I've got a factor of 1/3 on each side. So I can multiply both sides by 3 and get the same solutions. So now I have 1 on the cubed root of x cubed minus m cubed to the power of 2. So that's to the power of negative 2/3, 1 divided by the cubed root of my thing squared. That's one way of evaluating this to the power of negative 2/3, or to the power 1 over to the power of 2/3. And on the other side, I'm going to get 1 over the cubed root of negative m cubed squared. So the cube root of negative m cubed, what number times itself is equal to negative m cubed? Well, that's negative m. If I square that, I get 1 over m squared. So now I have 1 over the cubed root of x cubed minus m cubed squared is 1 over m squared. That implies that the cubed root of x cubed minus m cubed, when I square that, I should get m squared. So that is equal to either positive or negative m. Now I can cube both sides here, and I get x cubed minus m cubed is equal to plus minus m cubed, which is plus minus m cubed. If I cube m positive m, I get m cubed. If I cube negative m, I get negative m cubed. So that's what this is equal to. And then xq is therefore equal to plus minus m cubed plus m cubed. Well, minus m cubed plus m cubed is 0, which just shows us that if x is equal to 0, then the derivative evaluates to the derivative at 0. That actually is the x-coordinate of p, but q is a different point of p, so we want the other solution to this equation, which is when we get positive m cubed plus m cubed, which is 2m cubed. So the other point, other than x equals 0, where the gradient of g is the same as the gradient at p, the y-axis intercept, is when x is equal to 2m cubed. So that's the x-coordinate. And then to get the y-coordinate, we just need to substitute the x-coordinate into the equation of the function. So g of xq is the cubed root of x, which is 2m cubed, minus k plus m. Now that's our function in terms of m and k, but we know that when it passes through the origin that k is equal to m cubed. So this evaluates to the cubed root of 2m cubed minus m cubed, which is 1m cubed. So the cubed root of m cubed, which is m plus m. So this is 2m. So just writing the final answer in green, q is 2m cubed, 2m. And that's the answer to part D, and that completes the exam.